Greetings students, as you've gone through the lectures corresponding to current electricity, we'll now try to work out some of the problems which we come across in competitive exams of your interest. So let's start off with the first problem. First problem states, three resistors R, 2R and 3R are connected in parallel to a battery. Then A. The current through each resistance is same. B. The heat developed in resistance 3R is maximum. C. The potential drop across resistance 2R is maximum. D. The heat developed in resistance R is maximum. It's given that we have a parallel connection. It means that the potential drop across each resistance should be same. Given this, we can say that C is a false statement. Using the same statement, I can say that the current through each resistance will be different, because same potential difference will give me different values of current for different values of resistance. Hence, A is also wrong. So our primary focus for this question is the heat developed. Heat developed is given by P is equal to V square by R. Given it's a parallel connection, I can say that P is proportional to 1 by R. So the resistance having the least value will have the highest heat developed. Hence, D is the correct option. That is, the heat developed in the resistance R is maximum. So let's move on to the second question. Second question states, two resistors R1, R2, given R2 is greater than R1, are connected in parallel. Their equivalent resistance R is, we know that 1 by R, capital R, is equal to 1 by R1 plus 1 by R2. Using this equality, I can write 1 by capital R is greater than 1 by R1. 1 by capital R is also greater than 1 by R2. Using these two inequalities, I can also write that capital R is less than R1 and capital R is also less than R2. With this inequality, and the given inequality, I can write that capital R is less than R1 is less than R2. So this is the relationship between capital R, R1 and R2. The only expression which satisfies this relationship in given options are A. So A is my correct answer. So let's move on to the third question. Third question states, an ammeter reads up to 1 ampere. Its internal resistance is 0.81 ohm. To increase the range to 10 ampere, the value of the required shunt is. It's given that I have an ammeter of 0.81 ohm resistance. It can take up to 1 ampere. Now I want to increase its intake to 10 ampere. So I apply a shunt. Let's say it's of a value of R. So I have 0.81 ohm over here. So it's now able to take 10 ampere. So it means 9 ampere goes in this branch and 1 ampere goes in this branch. So I can write 9 ampere into R ohm is equal to 0.81 ohm into 1 ampere. That is, potential drop across my 0.81 ohm is equal to potential drop across my shunt resistance. With this, I can write that capital R is equal to 0.09 ohm. Hence, A is the correct answer. So let's move on to the fourth question. Fourth question says, if a wire of resistance R is melted and recasted to half of its length, then the new resistance of the wire will be. These kind of problem deals with finding out the dimension of the recasted wire. So let's say L and A be the dimensions of my initial wire, and given L by 2 is the new length of my wire and A dash be its new area. So applying the conservation of volume in this particular case, I can say that A times L is equal to A dash times L by 2. With this, I get my A dash to be 2A. So initially the resistance be R, which can be given as rho L by A. Now the new resistance is R dash equals to rho, its length is now L by 2 and its area is 2A. So I have rho L by 4A. Comparing R and R dash, I can say that R dash is 1 by 4 of my initial resistance. Hence, A is the correct answer. We'll now move on to the fifth question. It says, the potential difference between points A and B of the adjoining figure is. So here's my point A and here is my point B. To find out the potential difference between points A and B, I first need to find out the current flowing in branch A, B, C. So the current in the branch A, B, C is equal to potential difference across that branch, that is 2 volt, divided by the total resistance, that is 15 ohm. So I have 2 by 15 of an ampere flowing in the branch ABC. Now the potential difference across points A and B, let's denote it by VAB, is equal to the current flowing through it, that is 2 by 15 multiplied by the resistance across AB, that is 10, which gives me the value 4 by 3 volt. Hence B is the correct answer. Now let's move on to the sixth question. It says, an unknown resistance R1 is connected in series with the resistance of 10 ohm. This combination is connected to one gap of a meter bridge while a resistance R2 is connected in the other gap. The balance point is at 50 centimeter. Now when the 10 ohm resistance is removed, the balance point shifts to 40 centimeter. The value of R1 is in ohm. So let's draw the initial setup, that this R1 plus 10 ohm, this is R2, this is the wire of 1 meter. Now the jockey lies at the midpoint of it. So this is 50 centimeter and this is 50 centimeter. The new setup is, in this side it's R1, in this side it's R2. Now the jockey lies at 40 centimeter from one end and 60 centimeter from another. Now I will use the Wheatstone bridge principle on which this meter bridge is based on. So R1 plus 10 divided by R2 is equal to 50 divided by 50. Similarly, R1 divided by R2 is equal to 40 divided by 60. So with these two, I get R1 plus 10 equals to R2 and R2 equals to 3 by 2 of R1. Using these two relations, I can write that R1 is equal to 20 ohm. Hence, C is my correct option. So let's move on to the seventh question. It says, a cell of internal resistance 3 ohm and EMF 1 volt is connected to a uniform wire of length 500 centimeter and resistance 3 ohm. The potential gradient in the wire is, so the setup goes like this. Here I have 1 volt, here I have 3 ohm, and this is a wire whose length is 500 centimeter and whose resistance is 3 ohm. To find out the potential gradient across the wire, I first need to find out the current flowing across it. So I is equal to 1, that is the potential drop across the whole circuit, divided by the total resistance, that is 3 plus 3, which gives me 1 by 6 ampere. Now the potential drop across the wire is equal to V into current flowing across the wire into the resistance of the wire. So I get 0.5 volt, that is, this is the drop across the wire. Now potential gradient, let's say it's given by G, is equal to the potential drop across the wire V divided by the length of the wire L. So it's 0.5 volt divided by 500 centimeter. So my potential gradient is equal to 1 millivolt per centimeter. Hence C is the correct answer. So let's move on to the eighth question. It says two wires A and B of same material and same mass have radius 2r and r. If the resistance of the wire A is 34 ohm, then the resistance of B will be, it's given that mass of A is equal to mass of B. So I can write that rho, that is the density over here, that is the density of mass, multiplied by the volume of the wire A, which is, let's say, LA into 4 pi r square, the cross-sectional area, is equal to, again the same mass density, into LB into pi r square, again the cross-section area. So I have the relation between the lengths of A and B wire. So 4LA equals to LB. Let's call this as first equation. Now, resistance of wire A is given as rho r, that is resistivity, into LA divided by 4 pi r square. Similarly, RB, the resistance of the wire B, is given by rho r, its resistivity, into LB divided by pi r square. Now substituting the value or the equation 1 in this expression, we get RB is equal to 4 rho r LA pi r square. Now comparing RA and RB, we get RB equals to 16 times of RA. So substituting the value of RA, that is 34 ohm, we find out that A is the correct option. So moving on, 9th question. In the circuit shown in the figure, the current drawn from the battery is 4 ampere. If 10 ohm resistor is replaced by 20 ohm resistor, the current further drawn from the circuit will be. Now in the given circuit, I can see that this is 1 ohm, this is 7 ohm, this is 3 ohm, and this is 21 ohm. We can clearly see that the Wheatstone bridge principle, that is 1 by 7 for this and this, is equal to 3 by 21 for this and this. Hence, irrespective of what's the value of resistance connecting these two branches or these 2 points, the current across this branch is 0. Hence, D is the correct answer. Moving on to the 10th problem. 6 identical cells of EMF E and internal resistance R are connected in parallel. Then the net EMF and internal resistance of the combination will be. So the setup goes like this. Here is a cell of internal resistance E and R. Again the same. So I have like these 6 cells connected. So it's again E resistance R, E resistance R, resistance R. So I have 1, 2, 3, 4, 5, 6. We know that resistance when connected in parallel follows this rule. 1 by R is equal to 1 by R1 plus 1 by R2 till 1 by Rn. So in this particular setup, I can say that 1 by R is equals to 6 times of R. That is, my net resistance is equal to R by 6. EMF, that is the potential drop across these 2 points, remains the same for each branch. Hence, E is the potential drop, that is E net is equal to the EMF of each cell. So C is my correct option, that is the net EMF remains E, but the resistance falls to 1/6 of the internal resistance of the cell. So let's move on to the 11th question. It says, in the following figure, potential difference between A and B is. So here is my point A and here is my point B. To find out the potential difference between point A and B, we first need to find out the current in the circuit. So The net resistance of the circuit is 10 ohm plus two 10 ohm resistor in parallel, so it's 5 ohm. So I have 15 ohm as my net resistance. So the current in the circuit is equal to 30 volt, that is the potential difference in the circuit, divided by the net resistance. It gives out 2 ampere. Now 2 ampere actually flows in this direction. So being 10 ohm resistance in this and this, I can say that 1 ampere goes in this direction and 1 ampere goes in this direction. So the potential difference across point A and B is equal to VAB is current flowing across point A and B, that is 1 ampere, into the resistance, that is 10. So I have 10 volt as an answer. So B is the correct answer. Moving on to the 12th question. Which of the following does not obey Ohm's law? So copper is a metal, it obeys Ohm's law. Diode valve, it doesn't obey Ohm's law because of its reverse and forward bias nature. So this does not obey Ohm's law. Aluminium, it obeys Ohm's law because it's a metal. So B, being wrong, it doesn't obey Ohm's law, is the correct answer. Moving on to the 13th question. It says there are 3 voltmeters of same range but of resistance 10,000 ohm, 8,000 ohm and 4,000 ohm respectively. The best voltmeter among these is the one whose resistance is 10,000, 4,000, 8,000 or none of these. We know that greater the value of the resistance, the better will be the voltmeter. Hence A, that is 10,000 ohm, is the best resistance among the 3 given voltmeter setups. So A is the correct answer. Let's move on to the 14th question. It says the internal resistance of a cell of EMF 12 volt is 5 into 10 to the power minus 2 ohm. It is connected across an unknown resistance. Voltage across the cell when a current of 60 ampere is drawn from it is. So first we draw the circuit diagram corresponding to it. That is, this is 12 volt, this is 5 into 10 to the power minus 2 ohm. It's connected to an unknown resistance of, let's say, R. We need to find out the potential across the cell. That is, let's say this is our 2 points A and B. We need to find out what is VAB. VAB is actually equal to E minus IR. I being the current which is flowing in the circuit, R being the internal resistance of the cell. So it's 12 volt minus 60 into 5 into 10 to the power minus 2. So this comes out to be 9 volt. So VAB, that is potential across the cell, is 9 volt. Hence B is the correct answer. So let's move on to the 15th question. It says, when a piece of aluminium wire finite length is drawn through a series of dies to reduce its diameter to half of its original value, its resistance will become, so let's say the initial length be L and area be A. Now the final, so this is initial, the final state is, we have no idea about its length, but its diameter is half. So we can say that the area is being now reduced to 1/4 of the original area. So area is A by 4. We know that the volume of the initial and the final aluminium wire has to be same. So L into A equals to L dash into A by 4. Implies L dash is equal to 4 times the initial length. So the resistance, let's say the initial resistance Ri is equal to rho L by A. The final resistance, which is Rf, is equal to rho into 4L divided by A by 4, which gives me Rf is equal to 16 times rho L by A, or Rf is equal to 16 times R initial. So D is the correct answer. Let's move on to the 16th question. It says the number of dry cells, each of EMF 1.5 volt and internal resistance 0.5 ohm, that must be joined in series with a resistance of 20 ohm so as to send a current of 0.6 ampere through the circuit. So let's say I have this box which sort of denotes the cell, the dry cell which we are talking about. So it's 1.5 volt and 0.5 ohm. So I need to connect a particular amount of cells such that I do have a current of 0.6 ampere in the circuit, where this is 20 ohm and this is 0.6 ampere. So let's say I have n cells. I need to find out what's the value of n. So total potential in the circuit is equal to 1.5 into n. Total resistance in the circuit, R net, is equals to 0.5 times n plus 20, and the required current I is equal to 0.6 ampere. So we use the values of E and R and relate it to I, that is 1.5 n divided by 0.5 n plus 20 gives me 0.6. By solving this equation, we can find out that n is equal to 10. So we need 10 dry cells to extract 0.6 ampere when we are connecting those cells to a 20 ohm resistance. So B is the correct answer. So moving on to the 17th question. It says the resistance of a coil is 4.2 ohm at 100 degrees Celsius, and the temperature coefficient of resistance of its material is 0.004 per degree Celsius. Its resistance at 0 degrees Celsius is, so we know that RT, that is resistance at a particular temperature, is equal to R naught 1 plus alpha del T, del T denoting the change in the temperature, and alpha the coefficient of resistance. So RT is given to be 4.2 ohm. R naught, we need to find out what R naught is. So here's 1 plus alpha is 0.004, del T is 100 degrees Celsius, because this is 0 degrees Celsius and this is 100 degrees Celsius. So the change in temperature is 100 degrees Celsius. So 1.4 times of R naught is equal to 4.2 ohm, implies R naught is equal to 3 ohm. Hence B is the correct answer. So moving on to the 18th question. It says the value of R for which 20% of the main current passes through the galvanometer of resistance 80 ohm. So this is given to be 80 ohm. It says that 20% of the current, that is 0.2 I, goes through this branch and 0.8 I goes through this branch. So the potential difference across these 2 points needs to be same. Hence 0.8 I into R is equal to 0.2 I into 80. With this, I can find out R to be 20 ohm. Hence B is the correct answer. So moving on to the 19th question, it says 9 similar resistors of resistance R are connected as shown in the figure. Equivalent resistance between points A and B is, so this figure is kind of a prism, and we need to find out the net resistance between points A and B. So I have over here this prism, and here is a plane of symmetry. So I can say that the potential at this point and this point is same. So I can make this point coincide with this point. Similarly for this point, I can make this point coincide with this point. So the equivalent circuit diagram kind of looks like this. So here I have the resistance R, another R in parallel with another resistance R. Same goes for this branch. This is R, this is R. This is also R, and these are the points A and B. So this will give me R by 2, This will give me R by 2. This also will give me R by 2. So the next step in drawing an equivalent circuit diagram is this. This is R, points A and B, and this is 3R by 2. So if you now want to find out the equivalent resistance between points A and B, we can write it as 3 by 5R. That is, these two are in parallel, and if we solve it, we will get 3 by 5R as the equivalent resistance between points A and B. Hence, A is the correct answer. Moving on to the 20th question. It says, if switch S is closed at t is equal to 0, then the time at which the power supplied by the battery is equal to the rate of energy storage in the capacitor is, we know that the point at which we switch on this key, the power supplied by the battery is being distributed as the heat loss in the resistor and the energy stored in the capacitor. So for power supplied by the battery, that is PB equals to energy stored by the capacitor. For this to exist, heat loss by the resistor has to be 0. That is, I square R has to be 0. For this to be 0, I need my current to be 0. And this only happens at the steady state condition when T is very large. At a very large amount of time, we get I is equal to 0, that is, my capacitance starts to behave ideally. Hence, D is the correct answer. So moving on to the 21st question, it says potential difference between point A and B is. So in this given setup, I have 3 ohm over here, 3 ohm over here, 4 ohm, a current of 6 ampere passing through the 4 ohm branch, and again the 4 ohm over here. So I can say that the potential difference across these two branches are V. Let's call this as A and B. So VAB is equal to 4 into 6, that is 24 volt. So the current flowing across the 3 ohm branch will be 3 ohm branch, I3 ohm will be VAB divided by 3, that is 24 divided by 3, which gives me 8 ampere. So the total current flowing through this 3 ohm and this 4 ohm is equal to IT is equal to 8 ampere plus 6 ampere, which is 14 ampere. So potential difference across, let's say, point AB, that is, now my point of interest is this A and this B. Initially we used A and B for these 2 points, but in the question A and B are these 2. So right now we are dealing with this VAB, that's what's being asked. So VAB is equal to 3 into 14 plus 24 volt as we found out over here, plus 4 into 14, which comes out to be 122 volt. So A is my correct answer. Moving on to the 22nd question, it says potential of point B is, so this is my point B, let's call this point as 0 or O, and as we know this is grounded, so this is ground, and potential of this point V0 is equal to 0 volt. We need to find out what's VB, potential at point B. For solving these kind of problems, again we need to find out the current in the circuit. So current in the circuit, I is equal to 6 volt divided by 3 plus 2 plus 1 ohm. So this is equal to 1 ampere. So VBO, that is potential difference between point B and O, is equal to current in the circuit 1 multiplied by the net resistance across point B and O, that is 5. So I have 5 volt. We know that potential of point O is 0. So with this, I can say that potential at point B is 5 volt. Hence, B is the correct answer. So moving on. Next question. A battery having EMF E is connected to a variable resistance R. Internal resistance of the battery is small r. As we increase R, then potential difference across the terminals of battery in A increases, B decreases, C first increase, then decreases, D none of the above. So potential across the terminal of the battery, let's say, is denoted by V is equal to EMF of the battery minus current flowing in the circuit, that is capital E by small r plus capital R, times the internal resistance. So this gives me E times capital R divided by small r plus capital R. So this is the potential across the terminals of battery. And as we can see, if we increase the resistance, that is R, then the potential across the terminals of the battery also increases. Hence, A is the correct answer. Next question. Suppose the electric field between plate A and B is E1 and between plates B and C is E2. Then, so this is grounded, so we can say that these 2 points are actually connected because these are actually at the same potential, 0 volt each. And I have a sort of capacitor over here with one half of plate A forming one plate and the other half of the capacitor is formed by the other half of plate B. Similarly, the next capacitor is the leftover part of plate B and the half of plate C which is facing plate B. So the potential difference, or let's say VAB, has to be equal to VBC. It's a direct consequence of Kirchhoff's law. So E1 times L1 has to be equal to E2 times L2, implies E1 by E2 is equal to L2 by L1. So B is the correct answer. Moving on to the 25th question. If switch is closed at t is equal to 0, then the time at which the reading of both the voltmeters will be equal. So I have my resistance over here and I have my capacitor over here, and if I close my switch, the direct consequence of Kirchhoff's law states that the potential drop across the resistance has to be equal to the potential gain of the capacitor or vice versa. Hence, at all times, the reading of both the voltmeters will be same but opposite in direction. So the correct answer is D, all times. Moving on to the 26th question. It says, capacitor shown in the figure is in steady state. The energy stored in the capacitor is, so I have two resistors of R and R parallel to each other, and in one of the branches current I is flowing, and in the next half of the figure I have a capacitance of C and it's attached in parallel to a resistor R. So if the current I is flowing in this resistance, I can also say that the current I is flowing in this resistor also, because same resistance, they are connected in parallel, so they need to have same potential difference across it. So IR is equal to IR, same potential across these two resistors. So I can say that the current of 2I is actually flowing in this resistance because net current is 2I at this junction, and this capacitor is at steady state, so no current is flowing in this direction. I is equal to 0 over here. So potential difference across the capacitor is equal to VC. Let's call that VC is equal to 2IR, and energy stored in the capacitor is given by CV square by 2. So I have C over here, V square is 2 square, I square, R square by 2. So energy stored is equal to 2C I square R square. Hence B is the correct answer. Moving on to the 27th question. It says the maximum current that can be measured by a galvanometer of resistance 40 ohm is 10 milliampere. It is converted into voltmeter that can read up to 50 volt. The resistance to be connected in series with the galvanometer is, so I have a 40 ohm galvanometer which can read up to 10 milliampere. Now we need to connect some resistance in series with it such that it's able to read 50 volt, that is V is equal to 50 volt, and this has to be equal to 10 milliampere times, let's say, R plus 40. So solving this, it will give me 5000 equals to R plus 40, implies R is equal to 4960 ohm. Hence, B is the correct answer. Moving on to the next question. The resistance of an incandescent lamp is A. greater when switched off, B. the same whether it is switched off or switched on, C. smaller when switched on, D. none of these. Clearly, based on the working principle of incandescent lamp, C is the correct statement. And it's smaller when switched on. So C is the correct answer. Moving on to the 29th question. Two wires of the same dimension but resistivity ρ1 and ρ2 are connected in series. The equivalent resistivity of the combination is. So I have over here a wire whose length is L, A of cross section is A, resistivity is ρ1. It's connected in series with another wire of same dimension, length L, cross section area A, resistivity ρ2. So the net resistance R net can be said to be ρ1 L by A plus ρ2 L by A. So this is equal to ρ1 plus ρ2 times L by A. So this is my net resistance. To find out the net resistivity, I need to do this. R net is equal to ρ dash. Now the length of the wire is 2L, because this is of length L and this also is of length L. The area of cross section remains the same. So ρ dash 2L by A is equals to ρ1 plus ρ2 times L by A. This gives me ρ dash equals to ρ1 plus ρ2 divided by 2. Hence, C is the correct answer. Moving on to the 30th question. Identify the set in which all the three materials are good conductor of electricity. A. Copper, silver, gold. B. Copper, mercury, salt. C. Copper, silicon, diamond. D. Copper, germanium and mercury. So clearly copper, silver and gold are the best conductor of electricity. So A is the correct answer.